Welcome, everyone. We're going to start the preview of the new Materials Project website. My name is Cody O'Donnell, and I'm one of the developers of the Materials Project team. Today, I am going to walk you through a new version of the Materials Project website that our team is gearing up to release to the public. This website is still a work in progress, but you'll see an exclusive look at our progress so far today. Feedback from the Materials Project community is a really huge part of making the website better. So we've created the hashtag website feedback channel on Slack so that your voice can be heard directly. Feel free to share your thoughts, ideas, or questions about the website on this channel. I will personally be active inside that channel over the next 2 days, along with other members of our team to help facilitate discussion. To join this channel, click on Add Channels in Slack and find the channel called hashtag website feedback. Then click on the channel and click the Join Channel button. So what's covered in this talk today? During the demo, I will show you how to navigate the website, what kind of data we have available on the MP website, and how to effectively explore data on our new website. So with that said, let's jump into the new website. Now you should be seeing the homepage of the Materials Project website. If you're new to the Materials Project, the homepage is a good place to go to get an overview of what you can do with the Materials Project. At its core, the Materials Project website is a place for people to access the data produced by the Materials Project without the need for programming knowledge. If I scroll down, we'll see a high-level overview of the data that the website has available. You'll see the Materials Project database consists mainly of materials. Nearly all of these 140,000 materials are inorganic crystalline materials, but we also have data for over 21,000 molecular compounds and over 3,000 intercalation electrodes. All the data and properties for these materials, molecules, and batteries are based on calculations run by the Materials Project. To date, those calculations have accounted for around 1.7 million computing hours. And the primary method we use to calculate our data is called density functional theory, or DFT. We're not going to go deep into the methodology during this talk, but you may learn more about this method and DFT during some of the other workshop lessons. So now that we have an idea of what kind of data is in the Materials Project, let's start exploring. The first thing I'm going to do is scroll back up to the top and click the Login button on the top right of the screen. I could also click on the button here that says Login or Register. So I'm going to click Login now. Now I'm going to select which account I'd like to use to log in or register for the Materials Project. I'm going to select Continue with Google. And now I'm taken back to the homepage, and I'll see that instead of the login button in the top right, I see a user icon, and this means that I'm logged in. So now that I'm logged in, I'm ready to start exploring the data. I'm going to click on Start Exploring Materials. This takes me into the Materials Explorer, the primary app on the Materials Project website. Here I can search and explore materials in our database. You can see all of your search controls on the left side of the screen and your search results on the right side of the screen. Right now, you're looking at an unfiltered view of all 140,000 some materials in the materials project. So let's narrow down our results by searching for materials that include only silicone and oxygen. To do that, I'm going to go over to the search section near the top and use the periodic table to click on the symbols for silicon and oxygen. I chose to select the elements using the periodic table, but you can just as easily type them into the search box here. The hyphen separating the two symbols will tell the explorer to find materials that only contain these two elements. Now I'm going to click search to see my results. Now I can see there are 342 materials that include only silicon and oxygen. So let's do another search by elements. This time I'm going to search for materials that include only lithium, potassium, and oxygen. So I'm going to go back to the search bar at the top and type in Li-K-O and click search. Now I can see there are only 3 materials in the materials project database that include only lithium, potassium, and oxygen. So this search shows me materials that only contain these 3 elements, lithium, potassium, and oxygen, but I can also expand my search to include materials that contain at least lithium, potassium, and oxygen. To do that, I'm going to edit my search to use a comma to separate the element symbols instead of a hyphen. I'll click search again. Now I can see there are a lot more materials that match my search results. So far, I've only searched for materials by elements, but you can just as easily use the search bar to find elements by formula or ID. So let's do a search for sodium chloride. I'm going to go back to the search bar and type in the chemical formula for sodium chloride, NaCl. You'll see that because I'm typing a formula, a suggestion box will pop up with formulae that match what I've typed in so far. I know that I want to search for sodium chloride, so I'll click the first suggestion over here. Now my results include 3 different forms of sodium chloride. The reason you're seeing multiple materials with the same formula is because there are multiple arrangements of atoms or polymorphs that are possible for this chemical formula. Another common example of this is graphite and diamond, which are both carbon. So every material in the materials project database is assigned a unique material ID. If you look at our results table, you'll see the material ID for each result in the first column on the left. This is the unique ID we use to keep track of data for a specific material. It's important to know that we will always show the best data we have for a given material on the website. So even though the material ID will never change, some of the property values you're seeing in your results will change on the website as our calculations improve. If you already know the material ID for the material you're looking for, you can type that ID into the search box. So I'm going to search for a material that I know called MP-2715 and click enter. And now I see just that one material in my results. This material ID happens to be for cobalt arsenide, which we can tell by looking at the formula column. To perform even more advanced searches, you can use the wildcard element syntax. So let's go back to one of my previous searches, materials that include only lithium, potassium, and oxygen. For that, I'm going to go back up to the search bar, type in li-k-o, and click enter. So this shows me materials that only include these 3 elements. If I want to include materials that contain one additional element of any kind, I can add a wildcard. To do that, I'm going to modify the search by adding a hyphen asterisk to the end. If I click search, I'll see there are many more results now. And now my results are showing materials that include lithium, potassium, oxygen, and one other element. If I want to show materials that include lithium, potassium, oxygen, and 2 other elements, I can add another wildcard element to my search. So I'll go back up to the search bar and type in hyphen asterisk to add a second wildcard. Click search. And now I can see my results have changed by adding that extra element. You can also use the wildcard syntax when searching by formula. So instead of simply searching for sodium chloride, like I did before, now I'll search for all materials whose formula includes oxygen 3. So I'll type O3, one of any element. So I'll type in an asterisk for a wildcard, and one of another element. So I'll type in another asterisk for another wildcard. This particular formula structure is actually how you define perovskite structures, a certain class of compounds that all have the same type of crystal structure. And I'm going to click search to see those results. Note that when searching by formula, the amounts you specify are always taken into account. For example, look at how the results change if I search for O3 ** 4 instead. So I'll add a 4 to the end of my search. And now you can see that in the results, one of the wildcard elements will always have to have, there will always be 4 of that particular atom. So let's go back to our previous search for perovskite structures. I'm going to backspace that 4 and click search again. Remember that you can always use the periodic table to assist you in building searches. If I click the periodic table icon on the left of the search bar, I will reveal the periodic table again. Notice the dropdown above the periodic table. This tells you what mode the periodic table is in. Right now we're on formula mode because a formula was detected in the search box. This means that when I click elements on the periodic table, they'll be added to the search box in the formula syntax. In other words, without a delimiter between the symbols. I can switch modes at any time by selecting the dropdown. So first I'll clear out what I have in the search box already. Now if I select the dropdown and click elements at least from the dropdown, selected elements from the periodic table will now be added to the search box in the comma separated syntax for searching for materials with at least these elements. Okay, let's go back to that perovskite search. So far, we have only been searching by elements, searching for materials by elements, formula, or material ID. Remember that you can always get more information about how to use this top search bar by hovering over the question mark on the right. And so now we can refine our search even further by using the filters panel on the left. Notice that the entry from the search bar activated the formula filter in the composition section of the filters panel. I can use these filters to make quick changes to my search instead of using the search bar. All of the material filters are grouped into different sections in the panel on the left. Clicking on any one of the group labels will reveal the filters in that group. So let's filter down our results by crystal system. For that, I'm going to go down and open up the symmetry section and select an option from the crystal system dropdown. Let's select trigonal. If you look at the results on the right, you'll see that now we are only seeing materials with a trigonal crystal system. Any number of these filters can be activated together to make your search more specific. So let's add one of the thermodynamic filters to our search. I'll open up the thermodynamics section of filters, and we'll filter results by band gap between 2 and 5 electron volts per atom. I'm going to drag the slider to the values that I want. I can also use the text box to control the slider. So here I typed in 5 to control the upper bound of the slider. And let's also add a filter for formation energy. I'm going to filter our results to formation energy between -2 and 0. Now, if I look above the table, I can see that I have 4 filters activated. The formula filter we applied originally, formation energy between -2 and 0, band gap between 2 and 5, and crystal system trigonal. Now I want to point your attention to our table of results. You might have noticed that we've filtered our results down by formation energy, but we don't actually see formation energy in our results table. We can change that by going to the top right of the results section and clicking on the columns dropdown. Here I can customize which columns are showing in the results. I'm going to scroll down to formation energy and select it. And now I can see the column formation energy in our table. By default, materials are sorted by energy above hole, which is the column to the left of formation energy. Energy above hole is a useful number that assesses the predicted stability of the material. Here we are displaying energy above hole in electron volts, or EV, per atom. The units for a column will always be displayed in parentheses underneath the column name. So make sure to always take note of what units are being displayed in the table. 0 energy above hole means that material is predicted to be stable. Below 0.1 means that material might be synthesizable, and 0.5 EV per atom or more means that material is very unlikely to be synthesizable. You can change the sort column by clicking on the column header. So right now we're sorting by energy above hole. Let's instead sort by band gap by clicking on the band gap column header. Now I can see the materials with the smallest band gap at the top. You can sort in descending order by clicking the column again. You may also have noticed that certain materials have a star next to them. This star means that material has been experimentally observed In other words, it is known to be synthesizable. We determine this by matching our crystal structures with entries in the inorganic crystal structure database, or ICSD. If you're not familiar with the ICSD, it is the largest database for completely determined inorganic crystal structures. So if our crystal can be found in the ICSD, then we can be almost certain that the material has been synthesized before. To see more information about any material, you can click on the material ID in the table to go to that material's detail page. So let's check out the detail page for MP28873, the second result here in our table. So I'm going to click on that. And now we're at the material detail page for MP28873 for cesium bromate. You can think of this page as a one-stop shop for information about this material. And every material in our database has a detail page much like this one. The first thing I want to point your attention to are the breadcrumb links where it says, under where it says Materials Explorer. These links can help you orient where you are on the website. We can see that we are on the page for MP28873, which comes from the formula CSBR03, which is part of the chemical space BR-CS-O, which can be explored in the Materials Explorer app. Clicking on either the formula or the chemical space links will show you the other materials that exist in that space. One of the first things you'll notice on the detail page is the 3D crystal structure. You can interact with the structure by clicking and dragging to rotate the structure. The atoms in the structure are color-coded by element. In this structure, the cesium atoms are purple, the bromine atoms are dark red, and the oxygen atoms are red. You can hover over any atom to see what it is. Here you'll see the atom's element symbol and its Wyckoff label. You can enlarge the structure by clicking the expand button down below. I'm going to click that now. This also opens up several other options for customizing your view of the crystal structure. It's important to note that a crystal can look quite different depending on the unit cell you use to visualize it. We show crystals using their conventional cell by default, but you can also switch that at any time. And take note that this is different from our existing website where we would show the crystal as we computed it, which was usually in its primitive setting. Now I'll close this view by clicking the close button near the bottom. Next to the structure, you'll see values for several key properties of the material. Notice the energy above hole, band gap, and formation energy that we saw in the Materials Explorer. If I keep scrolling down, you'll see a brief description of the material. These descriptions are machine generated using one of our own tools we call the robo-crystallographer. If I scroll down further, I'll see additional information about the material's crystal structure. Here are the lattice parameters for the structure. Because of the method we use to calculate this property, these numbers can be off by 1 or 2%. So if the numbers look very off to you, this may be because you are comparing lattice parameters in different crystallographic settings. Right now, we're looking at the lattice in its conventional crystallographic setting, but you can also see the lattice in its primitive setting by using this drop down below here. So I'll click conventional and switch to primitive, and you'll see that the values of the lattice are now different. switch back to conventional setting. Notice also that some of the labels have a dotted underline. If you hover over one of these labels, you'll see helpful information explaining the information in that section. And this convention is used across the website to give you more helpful information about different parts of the page. So let's move down to the properties section of the detail page. If you look at the table of contents menu on the left, you can see which properties we have available for this material. You can click any item in this menu to quickly navigate to its section on the page. It's important to note that not all properties are available for all materials. Let's take a look at what we have available for cesium bromate. So the first property section you see is the thermodynamic stability section, where you have the thermodynamic stability data for this material. You'll see the property numbers on the left, and on the right, you'll see an interactive phase diagram. If you look at the top of the thermodynamic stability section, you'll see several different buttons. These are two links to the papers with the methods that support the data in this section. If I click on one of them, I can head over to that publication to read more. So I'll click Jane et al. And this takes me over to that particular publication. The other button that says understand this section is a link to our documentation. We're working on revamping our documentation, so some of these links will be disabled at the moment. But you'll see both of these kinds of buttons for each property section on a materials detail page. If I keep scrolling down, next we have the electronic structure section, where you'll see key property values as well as a band structure plot and density of states plot. You can make these plots interactive by clicking the Get Interactive Plot button below. So if I click that, now I can hover over the sections of the plot and see specific values. We also have the magnetic properties for this material, the piezoelectric constants, the dielectric constants. In the future, you'll be able to see X-ray absorption spectra for this material here, but this section is currently still in development, so it's blank at the moment. This material does not have any synthesis recipes available, but to show you an example, I'm going to go over to another material detail page I have open. So I'm going to go up to the top here to a different tab. And this is the material detail page for K2 TI409. Notice how the available properties on the left in the table of contents are different for this material. That means we haven't calculated all of the same properties for this particular material. And now if I scroll down to the synthesis recipes section, you'll see that this material does have synthesis recipes to display. Each one of these cards is a synthesis recipe that has been used by experimentalists to synthesize this material. This information comes from a collaborating project that has been able to mine synthesis information from literature directly. I'll show you more of this in the Synthesis Explorer app later on. For now, let's head back over to the cesium bromate page. I'm going to go back up to the different tab. Now we're back on cesium bromate. The next section we have is the suggested substrate section. And we have a computed list of suggested substrate materials for this current material. For each suggestion, the current material is considered to be the film deposited on top of the substrate. You can scroll through this table to see all of the suggested substrates that we've computed. Continuing on to the contributed data section. Here we have contributed data for this material. While the materials project produces a lot of data itself, users and collaborating scientists can upload their own data using the MP Contribs platform, and data shared via MP Contribs are associated with a particular material ID and displayed to the public here on the detail page. I can expand this entry to learn more about the contributing project by clicking See More. Here I can see a description of the project, its linked references, and the kind of data the project has contributed. You can click on the project link to see all the data the project has contributed, or you can click on the contribution ID up here at the top to see the specific data contributed for this material. You'll learn more about MP Contribs in a talk later in the workshop by Patrick. Skipping down to the external links section, you can see links to the ICSD or Inorganic Crystal Structure Database, as well as Wikipedia. Because the material we're looking at has been experimentally synthesized, it is logged in the ICSD using the unique ID you see here. And so we're able to match it and link to the page in the ICSD for this material. If you use data from this material in your research, you can cite it using the sentence we provide here. You can also see the DOI for the material here. Every material in the materials project database is given a unique DOI or digital object identifier, which is helpful to use for citation purposes. We also provide instructions on how to download the raw data for this material. Right now, you do this through the Materials Project API, which you're going to learn more about in another lesson later today. And now at the bottom of the detail page, we show materials that we have calculated to be similar to the one we're looking at. We calculate similarity based on the geometry of the material's crystal structure. So here we see 4 different materials that have a similar crystal structure to the one we're looking at. So much of the information you've seen on the material detail page can be further explored in some of our other apps. If I scroll back up to the top and go to the navigation menu, I can hover over the apps button in the navigation bar to see all the apps on the materials project. So let's look at the Synthesis Explorer app by clicking on Synthesis Explorer in the menu. Now we're in the Synthesis Explorer app. Here we have a search interface similar to the one we used in the Materials Explorer app. But now, instead of exploring materials, we can explore all of the synthesis recipes that we've mined from literature. On the left, again, I have my search controls, and on the right, I have my results of synthesis recipes. So if I'm interested in learning how to synthesize lithium aluminate, for example, I can enter its formula in the search bar to find recipes that synthesize this material. I'll go over to the search bar and type in the formula for lithium aluminate, LiAlO2, and click search. And now I can see there are 39 different recipes where lithium aluminate is the target material. Each of these results on the right comes from a published paper that describes the steps they took to synthesize that target material. Key information has been extracted from each paper so that users can easily discover recipes of interest. You can already see the target material and the precursor materials. In other words, the materials that are used in the reaction to produce that target material. But if I click see more, I can see more information about this synthesis recipe. Now I can see an excerpt from the paragraph in the paper where the synthesis procedures are discussed. I can see the full reaction equation for the synthesis recipe. I can see the exact synthesis procedures used in this experiment, which have been extracted out from the paper. And I can see this type of synthesis that is being performed. You can also click on the bottom link to see the full paper. So if I click down here on Sun et al., that'll open up a new tab and show me the paper where this synthesis recipe comes from. Just like the Materials Explorer app, synthesis recipes have additional filters that you can use to refine your results. For example, I can open up the synthesis procedures section of the filters panel and scroll down and filter our results by heating temperature used during synthesis. So if I'm only interested in synthesis recipes that use heating temperatures of less than 500 degrees Celsius, I can drag the right side of the heating temperature slider down to 500. And I'll see that that filter has been immediately applied. And only 21 synthesis recipes for lithium aluminate fit this kind of filter. Okay, let's move on to another app. For that, I'm going to scroll back up to the top, hover over the apps button in the navigation bar. So far, we've looked at how to explore materials and synthesis recipes. We have two other Data Explorer apps I'd like to show you, the Molecules Explorer and the Battery Explorer. First, I'm going to click on the Molecules Explorer. Here, we again see a similar search interface to the Materials Explorer, but instead of our materials dataset, we see our molecules dataset. From here, we can explore molecular compounds by several different properties related specifically to molecules. Let's search for a molecule by formula. I'll go over to the search bar and search for H8C5 and click enter. And now we see 22 molecules with this exact formula. If you look at the filters panel on the left, you can again see that the formula filter has been activated. I'll leave that for now and open up the basic properties filter to narrow down the results further. So I click on the basic properties section. And you can see we can filter results by electron affinity, ionization energy, charge, and point group. So let's include only molecules with the C1 point group. I'm going to go to the point group dropdown, click that, and select the first option, C1. And now you can see we're only seeing molecules in this C1 point group. And just like materials have their own individual detail pages. Molecules also have their own pages. I can click on any molecule ID in the Explorer to head over to its detail page. So let's check out MOL 38326, which is the first molecule in the results here. I'm going to click that link. So here you can see the chemical structure for this molecule, as well as some of its primary properties. We plan to add more detail to this page in the future, so keep an eye out for changes. And now let's check out the last of our Explorer apps, the Battery Explorer. I'll go back up to the apps menu and select Battery Explorer. If you're interested in batteries, the Battery Explorer is the place to go. Here you can explore our database of intercalation electrodes for a number of different battery specific properties, such as voltage curves. I can filter results down by a specific working ion. So I'm going to scroll down straight to the composition section of the filters. I'm going to open that up and find the working ion dropdown and select lithium. And now we're only seeing batteries that have lithium as its working ion. And you can also see in the battery properties section of the filters, there are a number of different properties that you can use to further refine your results. Okay. The Materials project has several more apps that let you combine data from different materials to enable more advanced analysis. So I'm going to scroll up and open the apps menu. Some of these apps are still in their early stages of development and aren't available to demo yet, but I'm going to show you our X-ray absorption spectra app as an example of another kind of app that we have. So let's check out that app by clicking on X-ray absorption spectra down here in the characterization section. Here in the X-ray absorption spectra app, we can explore all of the X-ray absorption spectra that the Materials project has computed and plot those spectra together. We calculate X-ray absorption spectra for every unique site in a material. So as a result, there are several 100,000 spectra in our database. Spectra that you select from the results table below will be plotted in this white box here at the top. You'll see that we have not selected any spectra yet. So let's go down and search the spectra. I'll start out by searching for a list of elements in the search bar. I want to show spectra for materials that only contain lithium, iron, and oxygen. For that, I'll go into the search box and type in Li-Fe-O and click enter. Now I can scroll down to the other filters and look at the absorbing element filter and choose one of the three elements in my list as the absorbing element. So I'm going to click on there and type in the symbol for lithium, Li. The K-edge filter was already activated by default, so I'll leave that as is for now. Then I'll select the spectrum type filter, and I'll set that to XANES, which stands for X-ray absorption near edge spectroscopy. So now I can see my 4 filters are activated here, filtering down the spectra. There are 44 spectra that match this search. And now, if I select the checkbox for any one of these spectra, the checkbox here on the left, those spectra will be plotted up on the top. So I'll plot the first 3 results by clicking on their checkboxes now. And now you can see those 3 lines plotted above. You can adjust the Gaussian smearing value, which simulates broadening seen in experimental X-ray absorption. I'll add 1 EV of Gaussian smearing now by clicking and dragging the slider to 1 EV. And you can see that that's modified the graph above. So that's it for the apps. Now I'd like to show you some of the more informational pages we have on the website to help you answer your questions and navigate the materials project. If you need help with anything related to the website or any other materials project tools, you can always go check out our documentation or our community discussion forum. To access those, you can go up to the top nav bar and click Help in the top right. This takes you to the help page where you'll find links to both the discussion forum and the documentation. To access the discussion forum, you can click on the discussion forum link here. So I'll click that now. The Materials Project Forum is part of the MatSci Community Discourse page, which is a shared space for discussion around several different material science research projects. The Materials Project Discussion Forum is really the best way to get your questions answered, both by members of the Materials Project team and other members of the community. I'm going to go back to the help page, clicking on the help page tab. You may also be able to answer your questions by checking out our about pages. For example, if you use the Materials Project or any of our apps as a resource in your research, you can find out how to cite us by opening up the About menu up here at the top and then clicking How to Cite. I'll go to that page now. Here at the top is the main citation for the Materials Project. And then down below, we have citations for any specific apps. So if you use any specific app and need to specifically cite that, you can use the citations listed for the app here. So that just about wraps things up. We've covered a lot of information in this talk, and I want to thank you all for your attention today. All the data shown on the website today can also be obtained via the Materials Project API. So you'll have another chance to familiarize yourself with the data that we looked at during this talk, during Jason's lesson later on today when he discusses the Materials Project API. Remember, you all can access the website now by going to next-gen.materialsproject.org. And I invite you all to continue to explore the website and share any feedback you have on the hashtag website feedback Slack channel. And I'm looking forward to talking with you all more. Thank you.
Thanks for that intro, Cody. This was a great demonstration of the new website and all the new capabilities. I can tell everyone that when we look at the new website and the old website, we're definitely itching to deploy the new one just because it looks so nice in comparison. let alone all the new features and upgrades that we've included in it that'll make both using it for access, direct access, as well as learning how to use the API and the data access capabilities much, much easier. Let me go ahead. What I'm going to do next is actually do a brief intro of CoCalc for the next lesson. So what I've shared here is the browser screen for CoCalc when you log in. There's the ability to choose different projects, and you should already have a project called the Materials Project Workshop 2021 with your name in front of it. This is the area that you'll use, or the project that you'll use to actually follow along with the next set of lessons, where you'll get a chance to actually use Python to do various activities that are material science related, such as building structures, manipulating them, and even building services and interfaces, and eventually using the API to get data from the materials project. So if I click on my project, it might ask if I want to start it. I'll have to click start. It'll go ahead and start the project, which will give me a container or a Python environment that I can use. Now, there's a couple different aspects of this project. At the top are a bunch of tabs for notebooks that have already been opened or are open. And I'm actually going to close these for now. You'll also see a bunch of toolbars up here that let you explore the files, create new files, or find files that you already have. So I go back to the Files Explorer. I'll see at the bottom that there's a traditional sort of file explorer or file tree that we can go through to look through different folders and find the lessons that we need, or the folders where we want to make our new empty notebooks so that we have the access to the data for the exercises that we'll be using. So for this example, let me click on the workshop folder. And you can see at the top right that now it's showing in the navigation bar a home icon and then a /workshop. This tells me I'm in the workshop folder. For this workshop, I can go to lessons, and in here are folders for each of the lessons that you'll see on day 2 and 3. If I click this name here, it will reorder the lessons by their name, so you can see them in 01, 02, 03, etc. If I click on 02 Intro to PyMatGen, this is where the first lesson this morning, or the second lesson this morning will be held. And this is where you'll want to create an empty notebook eventually in order to be able to follow along with the lesson that Roshi will be teaching. So if I want to now head back to the File Explorer and go up to the home directory, I can just click on this home button. That will take me back to the beginning, and I can explore, or I can go back into workshop at the bottom and find other lessons that I need to navigate to. So here, I'm going to click Intro to PyMatGen. And what I'm actually going to do in this folder is create a new notebook. Obviously, there are already existing notebooks in these lessons. Some of these are pre-filled out notebooks that have the lesson information. Some of these have exercises, and each instructor will tell you what the notebooks are for, so that you can use the appropriate one if you don't want to follow along in an empty notebook. There will often be other data files that are also included. These are just useful for the exercises or the lesson so that we can import in structures or import in data from calculations relatively easily. So for this example, just to show you how to use CoCalc, I'm actually going to make a new notebook. So I'm going to click the new up here, and this will give me automatically filled in a date time string that I can use. This is unique so that I can create new notebooks and not worry about overwriting old notebooks that I already have. And at the bottom, top left, you'll see a button that says Jupyter Notebook. This is the icon I want to click, and we'll have a new notebook. For some people, you'll actually be given a prompt asking you to choose a kernel, in which case you'll basically just click on Python 3, and that will give you the appropriate kernel. So in this environment, this is the CoCalc Jupyter environment. It's basically a version of Jupyter, which is a web interface to Python. In it, there are cells in which you can type in either Python code or markdown text. There is a toolbar at the top, just traditional toolbar like you'd see in Word or any other application in Windows, Mac, or Linux, and a bunch of buttons that do various operations in Jupyter. So I'm going to go ahead and click within the first cell and just do a very simple Python operation. I'm going to type in 3, hold down Shift and press Enter. That will execute that cell. So now Python is running and trying to run the code that just says 3. It shows the input here, and then it shows the output as well for cell number 1. So I typed in 3 and the output is 3. Very simple. I can click on this same cell and then I can Shift, return or enter again, and I can rerun it. And you can see that Jupyter has now told me it's run cell number 2. I can run any of the cells in any order that I want to. So I can run them out of order of the notebook if necessary. But typically our lesson notebooks are run in order to get specific outputs. So while you can go back and rerun cells, and that might be normal if you're developing new methods or exploring data with machine learning, you'll probably for the lessons today, just go sequentially from one cell to the next, Now this is a code cell. If I click on it and highlight the cell again, I can go to this drop down and I have 3 options: code, markdown, and raw. Code lets me run Python code. Markdown lets me write just documentation. So if I click on this, I now have a cell that's not going to run with Python, but just exist as sort of text within the Jupyter notebook. So if I double click on the cell again, I can type in any text. So this is some text, exclamation mark, Shift Enter, and that stores as text. This is a great way to have documentation within your code. When you're writing a new notebook, you're not writing documentation for somebody else. You're writing documentation for yourself a week, 2 weeks, 3 weeks from then, when you're not going to remember, why did I run this cell or why did I write this piece of code? That is the person you really want to target when you're thinking about documentation. Now let's show you how to ask for help. So in this next cell, I'm going to write some code that very clearly is going to break. I'm going to write 3 exclamation mark. I'm going to do Shift Enter. And when Python runs, it tells me you made an error somehow. Something is wrong. So what do you do if you need to ask for help in this situation? We'll go up to the top right corner and you'll see that there's a button called Chat. If I click on the Chat button, I will open a side panel in which I can ask for help. This is a chat that is only between yourself and all of the helpers and instructors in the lesson in the materials project. So no other attendee will be able to see this chat. You can ask help whenever you need to. So I will say, I need some help. And I'm going to do Shift Enter and run it. And I'll wait for one of the helpers or instructors to be able to come into my notebook. They will tell me that they can help me, and then they will go ahead and actually either fix the cell itself and fix the Python code and get it to run, or they will tell me something that will help me fix the code, such as you have an extra exclamation mark and extra parentheses. So I see a couple helpers, people who are in and actually looking at my notebook. I will ask one of them to respond in the chat and then fix the Python code and run it for me. So I'll just wait for that. While we're waiting for that, what else can we do within this interface? So if I look at this there we go, Victoria has responded and she's going to take care of this. We'll see that she's actually able to edit the code itself and run it for me. And then I can type back, thanks, at which point I can continue on with the lesson. So I'm going to close this chat window on the side by clicking on the chat button again. And now we're back to the full view of the Jupyter Notebook. On occasion, you'll have a situation in which Python is either stuck or you need to just reset your notebook and start over from scratch so that you can execute the first cells over and move on. In this situation, you can do one of 2 different things. You can click on the top right, the Python 3 image here. If I click on this, it will let me select a kernel. I can sit here and I can click on Python 3 and it will basically allow me to switch a kernel if I have another one. If you were in the primer lesson yesterday, you'll learn how to make a new environment and change your kernel. When you change your kernel, you've reset your notebook. The other option, which is what you'll probably use for the Jupyter lessons today and tomorrow, is click on the kernel button at the top toolbar and click restart kernel. If I click this, anything that I've previously run is therefore gone. So if I click restart kernel, it'll ask me, are you sure? I want to restart the kernel. And now if I scroll up and type in shift enter, you'll see that Python has told me that this command or this bit of code 3 is only being run for the first time. I've given myself a clean slate. This is one way to reset your notebook if something is going wrong where some bit of code is, say, using up too much memory and you don't know what's going on. The other option is you can run something if Python code is running in the background and you can't tell what's going on and it doesn't stop, you can click this kernel button and you can click halt. That will stop whatever is running. Again, it says, do you want to kill what's running? And then you say halt. And that will halt the kernel. So that will just say, okay, we've stopped whatever is running. This is another good way to keep things to keep going on. Both of these buttons on the toolbar are also very useful for this. So when I have a bit of code here, I can press the run button instead of shift enter. That will run that bit of code. I can press stop to stop some running code as well. So if I click this, click run, oh, it's going to go too quickly in 0.011 seconds. But if I have code that is running and I'm waiting, I can interrupt it by pressing stop. So this is the way to do this in the most safe possible way, in which you don't want to lose anything that's happening. You just want to stop the bit of code that's happening currently so that you can try to rerun it or fix whatever is wrong. So these are sort of the simple ways to navigate this space, and it will allow you to be able to run your own code today during the lessons that you'll have the rest of the day, as well as the lessons tomorrow. If you have any other questions beyond being able to navigate and use CoCalc, I recommend you actually ask these in the Slack channel itself. The Slack provides us with history. It lets us other people look at the same questions. So if multiple people have the same question, we can answer everyone at once. And it's a central place in which we can not only answer questions that are related to the materials project workshop, but also related to, say, material science or other topics such as the website feedback, which Cody was talking about.